Welcome back. This is part 2 of the Nash Equilibria in 2x2 simultaneous move games. In this game, we have two Nash Equilibria. We have BX and AY. Let's go through all four possibilities and see why. Well, at AX, both players are going to regret their choice, right? If X is played, player 1 would regret playing A because had she played B, she would have gotten 6, while with A, she only gets 1. Similarly, if A is played, player 1 would regret playing X and getting only 0 because had she known A would be played and she played Y, she would have gotten 3. So it only takes one player to have regrets for something not to be a Nash Equilibria, but both players in this case regret AX. What about BX? Well, if X is played, player 1 is quite happy playing B over A, because if you play B, you get 6, whereas if you played A, you got 0. Likewise, if B is played, player 2 is quite happy playing X over Y, because if you play X, you get 9, whereas if you play Y in response to B, you only get 0. So BX definitely is a Nash Equilibria. Let's now look at BY. Not a Nash Equilibria, because if Y is played, player 1 would regret playing B and getting only 1, where she could have played A and gotten 4. So because player 1 regrets BY, that's enough for it not to be a Nash, but as a bonus, player 2 also regrets it, because if B is played, player 2 regrets playing Y and getting 0, because had she played X, she could have gotten 9. Now, AY is a Nash, and this, like the game we did at the end of the last series, the last lecture, this is counterintuitive Nash. But it is a Nash because given what the other person does, neither player regrets his or her choice. You see, if Y is played, player 1 is better off playing A than B, because if Y is played and you're player 1, you play A, you get 4, whereas if you play B, you only get 1. So if Y is played, player 1 is happy playing A. Similarly, if A is played, player 2 would have gotten 0 from X, but gets 3 if she plays Y, so she would certainly rather get 3 than get 0. So neither player regrets what they did if they end up here. Now, I know, yeah, both people do better if they end up at BX than at AY, so isn't it stupid to call this a Nash Equilibrium? Well, that's actually confusing what a Nash Equilibrium is. A Nash Equilibrium is not the set of socially efficient outcomes, excuse me, or even the set of outcomes we think players will reach. Nash Equilibria is a technical term. There's a lot of math behind it. But in this kind of game, the simple way is to say no one regrets their choice given what the other person did. In this Nash Equilibria concept, you think what the other person's going to do is totally beyond my control. All I can control is what I do. Did I make a mistake given what the other person has done? Again, if player 1 plays A, player 2 certainly doesn't make a mistake playing Y over playing X. And if player 2 plays Y, player 1 doesn't make a mistake playing A and getting 4 compared to playing B and getting 1. So AY is definitely a Nash, as is BX. Let's go to another game. All right. In this game, BY is the obvious Nash Equilibria. First, everyone's getting their highest possible payoff, so of course you don't regret an outcome. You don't regret your choice if it led to your highest possible payoff. But AX is also a Nash Equilibria. Part of the reason is because when I say you don't regret your choice, that includes ties. So if X is played, if I play A, I get 1, and if I play B, I get 1. I don't regret A because I couldn't have done better doing something else. So when I say no regret equilibrium, I basically means what you're getting is greater than or equal to what you could have gotten if you'd done something else, given the other person's strategy. So if X is played, player 1 doesn't regret playing A because, you say, well, look, if X is played, I would have gotten the same playing A or doing the other thing I could have done, so I don't regret doing A. And if A is played, player 2 doesn't regret playing X because, if A is played, you get 1 playing X and you get 1 playing Y. So AX is a no-regret equilibria. Now, BX, that is not a Nash equilibrium. So before I explain, tell me who regrets if you're at BX. Think to yourself, which player regrets if they're at BX? And by regrets, I mean, player 1 writes down B, player 2 writes down X, they reveal. Who's going to say to him or herself, gee, had I only known what the other guy would have done, I would have done something different. So who regrets? Let's see, does player 1 regret? Well, given that X is played, no, 1 doesn't regret playing B. But player 2 does. If player 2 knew B was going to be played, player 2 is very unhappy with her decision to play X, because had she played Y, she would have gotten 6 more. Similarly, AY is not a Nash equilibria because if Y is played, player 1 will very much regret playing A and getting only 1, whereas if she played B, she could have gotten 7. Now, I admit I wouldn't expect real people who understood the game to ever get AX. And the only time you'll ever play A is if you're 100% certain the other person's going to play X. And you can never be 100% certain of anything in life. So yeah, this is a completely unrealistic outcome. But when I ask, or when your teacher asks, is it a Nash equilibrium, that's different than is it a reasonable outcome. Often the set of Nash equilibria equals the set of reasonable outcomes, but not always. And this is a case where, despite being a Nash equilibria, it's not a reasonable outcome. My opinion, the set of Nash equilibria is strictly greater than the set of reasonable outcomes. So every reasonable outcome is a Nash equilibria, but not all Nash equilibria are reasonable outcomes. Okay, let's go on to another game. Here, doesn't matter what you do, and everything is a Nash equilibria, right? How could you regret what you do? You get 3 no matter what. So if you're indifferent among all your strategies, everyone's indifferent among all your strategies, everything is a Nash equilibria. Easy. Final game. This one doesn't have a Nash equilibria. Let's see why. AX. Who would regret this? Well, player 2 would. Because look, if A is played, player 2 plays X, gets only 0. Had she played Y, she would have gotten 8. So AX, definitely not a Nash equilibria. What about BX? Now player 1 regrets. If X is played, player 1 regrets playing B and getting only 0, where she could have played A, gotten 7. So if you find out X was played, you're player 1, you played B, you're like, darn it, I wouldn't have done that had I known. What about AY? Who regrets here? Well, it's player 1 again. If Y is played, you play A, you get 0. You play B, you get 7. So you're player 1, you end up here, you'll say, gee, I made a mistake. Had I correctly predicted what player 2 was going to do, I wouldn't have picked A. And finally, down here, it's player 2 who regrets. Because if B is played, player 2 does better with X than with Y. So this game has no Nash equilibria, or at least not yet. Later on in the series or in whatever course or book you're looking at, we'll learn about mixed strategies, and that's where you can randomize, and that's where you can say not just play A or play B, but maybe play A 10% of the time and B 90% of the time. And it's going to turn out, if you allow for randomization, in every single game like this, there exists at least one Nash equilibria. There could be more than one, but there's going to be at least one if you allow players to randomize. But if you don't allow randomization, you might get 0 Nash equilibria. So let me just review. What is a Nash equilibria? Nash equilibria is a no regrets outcome where both players say, given what the other person did, I'm happy with my choice. Nothing else I could have done would have gotten me a strictly bigger payoff, given that I have no power over the other person, and given that my move couldn't have affected the other person. Because in games like this, you're moving simultaneously, so whether you write down A or B can't affect whether the other person's going to write down X or Y. Thank you, and goodbye for now.